This video is about generalization and overfitting. Consider that we want to estimate a function based on observed data points. For example, given the age of a person, we want to estimate how tall that person is. We are given some data points and aim to find a function that captures the relationship we seek to model. In general, we can model each data point by some input x and an output y. Let's consider polynomial regression. Using polynomial regression, we can find a better fit to our data by increasing the degree of the polynomial that we fit. In fact, adding enough terms, we can find a line that perfectly fits our data. This is called polynomial interpolation. To see why this is the case, let's take our data points and group them into a matrix. Similarly, we group their corresponding output into a vector. Here, n refers to the number of data points in our data set. If we write down the linear system of the regression in this notation, we note that we are guaranteed to find a solution if the rank of the design matrix is equal to n. Note that for linearly independent features we can achieve this by increasing the number of features d. Let's go back to our example where we interpolated our data points. Is this really a good solution? Pause the video and see whether you can see the issue with this approach. Looking at what we aim to model with this function, the given solution suggests that people go through a period of alternating growth and shrinking in the middle of their lives. Moreover, the solution suggests that people will experience a spike of growth shortly before they die. This seems to be very far from reality. Put differently, if we were to collect more data, such an approximation is likely to incur a large error on this new data. Let us see how we can formulate this more rigorously. Our data comes from an underlying distribution P. That is, every time we sample some data point we get a slightly different look. If we now have some approximation f hat, this approximation will experience a loss on a given data sample. We can then define the expected loss of the approximation by taking the expectation over the underlying data distribution. This is sometimes also referred to as risk. Unfortunately, we cannot calculate the expected loss directly as we do not know the probability distribution P. What we can calculate instead is the empirical loss by taking the average over our data set. Note that by the law of large numbers this quantity approximates the expected loss if the size of our data set tends towards infinity. Therefore, the more data we have, the better we will be able to estimate the expected loss of our approximation. However, normally we have to stick to the data we are given, since collecting more data can be expensive or infeasible for other reasons. So how can we get an estimate of the performance of our model without collecting new data? Pause the video and see whether you can come up with a solution yourself. We first note that we cannot take the data points on which we train our approximation. As discussed earlier, for any set of points we can find an approximation that fits the given data perfectly, thereby achieving an empirical loss of 0. However, this is not the expected loss of the model. In general, the loss on the training data underestimates the expected loss. To get a better estimate we need to evaluate our approximation on data that we did not use for training. To do so, we can partition the dataset into two disjoint subsets dt and de. dt is used for training our approximation by minimizing the corresponding empirical loss, while the de is used to evaluate our approximation. This is called a train evaluation split. Typically one uses around 80% of the data for training and 20% for evaluation. If the evaluation loss is much larger than the training loss, this is normally a good indicator that the model has too much capacity and starts to fit the noise that is inherent to the training data instead of the underlying function. This is what we call overfitting. We can address overfitting by gathering more training data to better capture the noise, or by using a simpler model. However, if the model is too simple, it won't be able to fit the underlying function. This is normally reflected in a large error on the training set, and is commonly referred to as underfitting. Note however that a large error alone is not enough to say with certainty that our model is underfitting, as the data distribution might just be very noisy. Here for example one could argue that the approximation fitted the data distribution perfectly, even though it has a high loss. So how can we figure out what might be a good model if we are only given a dataset? Pause the video and think how you would address this. One way to go about it is to consider what we know about the domain we are trying to fit, and limit our model accordingly. In our h to height example, we saw that polynomials of too high a degree lead to oscillations, which is not what we see in the real world. We therefore might want to only consider polynomials of limited degree. However, even if we don't know anything about the domain, we can estimate which model might work well. To do so, we split our dataset in k-disjoint subsets, indicated in color here. We then train an approximation on the union of k-1 of these subsets, and evaluate it on the remaining subset. We repeat this k times, with each subset used k-1 times as part of the training data and once as evaluation data. The resulting evaluations can be combined to get an evaluation of the model. This is also known as cross-validation. A similar evaluation can then be done for other models. In the end, we can pick the model class that gets the best evaluation. Let us summarize the main insights of this video. Given a set of points, we can always find a model that is strong enough to fit the points perfectly. However, such an approximation is likely to not perform well on new data points sampled from the same distribution. To formulate this insight, we talk about the expected loss, or risk, of a model. We can approximate this quantity by evaluating our function on a previously hidden evaluation set. Instead of performing the train evaluation split only once, we can also split our dataset into k subsets, using each of them once for evaluation. This cross-validation can then be used to get an evaluation of the model class to decide how powerful we should choose our model. Thanks for watching this video.